Okay, everyone should be to page 274. 274. We're going to be talking about piecewise functions today. If you brought your book, get out a blank piece of paper and use a blank piece of paper, please. You guys need to piece of paper up. Oh, you're on there. Is there anyone who could let Louise and Gerardo borrow?
Where do we write that?
You guys will get that one each.
I'm sure which.
I just need to start making like separating my. I think it's coming back.
Turn to page 274. It's blank spots under solver. Yes. No, some people didn't have their book. So if you did not bring your book, you still need to write the notes down on a blank piece of paper. If you brought your book, you're just writing the notes directly in the book. So we're on page 274, and we're going to be talking about something called a piecewise function today. A piecewise function. So they gave a definition in your book, but it's a very lengthy and wordy definition. So I gave you a different definition that will be a little bit easier. So in that big blank spot under solve it, you're going to write this definition. A piecewise function is two or more functions graphed together using only small pieces of each graph. So a piecewise function uses more than one graph at a time, and we only use small pieces of each graph. So in your book, in that key concept box, it already has this picture, but I just wanted to talk about the picture. So this is an example of a piecewise function. This is what the picture would look like. So, 274. So this is an example of a piecewise function. These, we could have drawn them as the entire line. I could have continued this on and said, oh, there's one line, there's a picture of one line, there's a picture of another line. But in order to make it piecewise, we didn't want them to cross or to cover the same area at all on the graph. So we erased some of it. We got rid of those pieces of those lines. And again, that picture is already in your book. You don't have to redraw the picture. It's at the bottom. I just wanted to talk about it. But I do want you to write in your book what the notation is like for a piecewise function.
It's already in there.
I wrote it a little bit differently. So when we know something is a piecewise function, the first way we know it's a piecewise function is if it has those braces. That kind of curly bracket is called a brace. Okay? That brace means we're working with more than one function at a time. So then first they give you a function you're working with. These are telling you what to graph. A function is what we actually graph. So they gave us, or I gave you two functions here. I just named them function 1 and function 2. Guys, please. You could also have a function 3, a function 4. You can have as many pieces of functions as you want. Most of the time we work with just 2, sometimes 3 pieces. And then another very, very key important part is where to graph. It's going to say 4 And then it'll say x greater than or x less than. That's why I left it blank, because it can change. And then it'll give you a key point, a very important number. So this where to graph is very, very important for our piecewise. It tells us what part of the graph do we keep and what part of the graph do we erase, what part of the graph do we get rid of. So we're going to go through a problem on the next page, page 275 at the very top. We're going to go through that problem and talk about how would we actually graph a piecewise function. Does everyone have this written down before I go to the next page, though? Okay. So on the next page, if you have your book already, it's already written down. You don't need to rewrite it. Come on. I don't know why it's, there we go. But on your graph itself, it didn't include the coordinate system. We want to put our axes on there so we know where the center of the graph is. And just kind of center it. We want it just in the middle.
Well, where do we start?
So again, now we're on page 275, so we can do this example problem. So when we're working with our piecewise functions, this, where we graph, is super important. This number here is one of our key points that we have to worry about. That -1 is where that jump would occur. If you look at the one that's already graphed on the bottom of page 274, there's a spot where it jumps and it switches from one graph to the other. Well, that key point tells us where that jump is going to occur. So it tells us before -1 is one part of a graph. After -1 is a different graph. So when we graph anything and we don't know what it looks like, the best way to graph it is to make a table. If you ever have a function that you're not sure what the picture is going to be, you can always make a table to get an idea of the picture. That's how mathematicians who were working with this function started with. So when we make this table, the problem is we actually have two functions we're working with. So I'm going to kind of split this table in half because we have two different functions we will be working with. And then that key point, again, is kind of where we base all of our x values off of. This key point is going to be used in both functions. We need that information for both functions because we need to know where does one function end, where does one function begin. So that key point, and that key point can change. On practice A problem 1, what's the key point for practice A problem 1 is underneath what we're working on. Okay, I heard this middle table say -2. That key point can change. That key point can change, so the other points we pick around the key point can change as well. So when we pick our points, we want to pick points bigger than the key point and smaller than the key point. And we want to pick stuff nearby. I could pick 100. 100 is bigger than -1. But that's too large to fit in my table, or in my picture that we have.
0, 1,
So 0, 1 is probably the closest points. Dalton is correct. Okay. What about points nearby -1 but smaller?
-2 and -3.
-2 and -3.
Miss Barman,
Yes.
can I go get Andromeda
Where is she?
at her house?
No.
Are you crazy?
No, you cannot. Okay. So, again, when we make a table, we get to pick our x values. How do we find our y values when we make a table? Rachel? We plug it into the equation, but here we hit a snag. We have two equations. So how do I know which one to plug it into?
because
Well, they gave us some other information here by our key points. Jaren.
well, the ones that are gray, they'll be that
Okay.
-4.
if our symbol says greater than here, which set of points was our greater than set of points? The top one.
Greater.
So this one would go with function 1. Those 3 points are going to be plugged into function 1 because function 1 had the greater than symbol on the where to graph. So then, where would we plug these points?
Negative.
Function 2. So when I say function 1 and function 2, I'm just talking about these pieces here. That's a function, that's a function. I'm calling this one function 1. And this one function 2. So now, we get to just plug these in. Yeah, it's a little confusing on how we set up our table, but we've practiced plugging in points before, last year and this year. So if I'm going to plug in these points into function 1, we know function 1 is negative x plus 4. Everywhere I see x, I'm going to replace it with one number at a time. I have to do this 3 times because I have 3 points that are going to be plugged in. So if I plug in positive 1, Dalton is correct. Negative 1 plus 4 is 3. Then I would plug in 0, and I would plug in negative 1. I'm going to have you guys do that yourself. But first I want to talk about the second half. So the second half we're working with the other function. We're working with the negative 3x minus 1. But it's the same idea. Everywhere I see x, I'm going to replace it with the number I'm working with. What number are we working with first?
Negative 1.
Negative 1. Now this time I have a little more to do to simplify. I have parentheses, which mean multiplication, and I have minus, which means subtraction. Which one do I do first, multiplication or subtraction? Multiplication. So negative 3 times negative 1 is positive 3. Minus 1 is 2. So I want you guys to finish this table. Don't draw the picture, because drawing the picture itself is an entirely different thing that we need to talk about first. But finish your table. I'm going to give you about 3 minutes. Okay. So now we've completed our table. We need to draw the point. Okay? So, we need to actually plot these points, which is a pretty easy task. 1, 3, we go right 1, up 3.
See, ours is in the graph.
You have to put the axes in yourself. Just draw them in.
Can we tell YouTube a story?
No. But you can quiet down so people can hear. Matilda, I need you to quiet down.
Once upon a time.
So, guys, we plot our second point, 0, 4. And we plot our last point, negative 1, 5. Now the question is, do I start with this right dot and go up and to the left? Or do I start with the left dot and go down and to the right? Because we're only using a piece.
Wait, say that one.
I think it's on the right.
Do we start on the right and go to the left?
Both.
Start on the left.
It's
Go to the
on
right.
No, go to your right.
because no, it's on the.
It's going up. It's going up.
Yeah, it has to go up.
Okay? Greater than, what direction is greater than?
Up or right.
To the right.
Sure.
So, and another way to think of it is we always start from our key point. When we draw our graph, we always start from our key point, which was negative 1. So we start here, go to the right. So now the second problem is, what about, there's a hole on, if you look at the one that's already drawn, there's a hole there in one of the points. We need to also be able to,
It's an outsider.
not right now, we can come at the end of class. Okay. Thank you. I thought you were just here to show me an assignment. Okay. So, Need your attention back up front. This point is going to have an open circle when we draw it. And the reason why, Logan, Kenny, the reason why is looking at these two symbols. What about this symbol would tell me don't include -1? It's less than, not less than or equal to. So when that happens, we leave an open circle. So when we graph the point -1, 2, we have to do an open circle. Steve, Demetrius.
Wait, why do you do that?
Okay. So again, the reason we use an open circle there is because when we look at what this information for our key points was, one said include -1, one did not include -1. And that could change. Sometimes it's the first one we draw that would have the open circle. Jaron, Gerardo, please quiet down. So now we plot the rest of our points. -2, 5. -3, 8 will go off your graph. That's okay. And then we always start from the key point. -1. Then we have to travel through the other points. Steve, can I have your iPod, please? I've had to ask you 3 or 4 times to take your headphones out. And then once we've graphed it, we are finished with the problem. So I want you guys to try an entire problem yourself, going through figuring out what points do we use on the table, how do I find my y values, and how do I draw my picture. So on the practice A, problem 1, I want you to do that entire problem. It's right below the problem we just did. So practice A, problem 1. I'm going to give you 5 minutes to go through the entire problem. So when we make our table, what are our key points that we should put on the break of the table? -2s. Then we just pick nearby numbers. So what should we pick above? Okay, what about below? Now, I could have picked -2, 0, 2. That would work as well. They're all bigger than -2. But usually we just pick what's nearby. Jaron, Miguel, Demetrius. Okay, then we had to figure out what function do we plug them into to get the y values. These were bigger than -2, so which one do I use? Top one. And since the top one does not have a line underneath, that -2 is going to be where our hole goes on our graph. So then we plug them into that top function. We would get 2, 3, and 4. We plug them into the top function, we get 2, 3, and 4. The rest we plug into the bottom function, we get 2, 1, and 0. Then we plot our points. Our point first was 0, 2. Second point was -1, 3. Third point is -2, 4. That's where our hole goes on our graph. And when we draw our line, we always go from that key point. That key point was -2. So if I start at the point -2, 4 and I draw my line so that I can go through those points, it'll go to the right. Then we graph the other points. -2, 2. -3, 1. -4, 0. Start from the key point and go through the other dots. Now there's a special piecewise function that's often used in word problems. And that is called the step function. This is on page Problem with the book is we have to jump around a lot, but we're going all the way to page 277. 277 for the step function.
Why?
We gotta take a power trip.
Okay, page 277 talks about the step function. So with the step function, it has a whole new notation that you've never seen before. If you look in that blue box, it gives a lot of information about the step function. And then it says y equals, and it gives us brackets around our x. Those brackets tell us to do something mathematically. So this is the step function, or you could call it the floor function, or you could call it the greatest integer function. What this means, so draw an arrow pointing to the y equals bracket x. What it really means is to round every number down to the closest integer. So round down to the closest integer. I would put that near the blue box. That's what our step function means. Or if it's already an integer, leave it. If it's an integer, we don't need to change it to get it to an integer. What do I mean by an integer? That's my next question, Dalton. Okay. That is reasonable. I can see where you're getting that from, but let's get a little more specific. What do we mean by an integer?
Number section.
Okay. Okay, but what kind of numbers are intersecting on the graph? Whole numbers. Okay. Guys, I need you to quiet down still. This is why we're getting a new seating chart next
So
time.
integer is a whole number on a graph.
Okay? A whole number, it doesn't even have to be on the graph, but the intersections on the graphs are made up of whole numbers. A whole numbers that are positive or negative. An integer is just any whole number that's positive or negative. So that floor function is telling us to round down to the closest integer. The reason we would do this, let's say I want to predict how many students I'm going to have in my class next year. So I go through, I gather the data, come up with an equation, and I say, okay, next year in every class, I'm going to have 35.6 students per class.
How do you have 0.6 in student?
How do you do that?
Okay? So, the question is, how do I have 0.6 of a student? I can't. Well, can I round that up and say I'm going to have 37 students? Can I take 0.6 of a student and say, oh, that person's really going to round up to a person?
No, you just gotta make it elementary.
Okay? We just have to get rid of the 0.6 completely and round down because we can't take part of a person and make them into an entire person. So, these floor functions are when you cannot take whatever object you're working with and actually split it up into pieces. I cannot take a person and split them into pieces and consider all the pieces a whole person. If I cut off my arm would not be considered an entire person. So that's why we would use these step functions. So the got it problem says f of x equals 2 bracket x. We're going to ignore the 2. We need a picture first before we can even work with changing the picture. So scratch out the 2 in your book. You don't need it, so that you're not confused when you look at your book later. And again, if we have no idea what the picture looks like, what should we do to get an idea of the graph?
We should.
What did we do for our piecewise? X and Y, we make a table.
So,
Okay, this time we don't have multiple pieces. Jaren, Matilda, This time we don't have multiple pieces, so I'm just going to pick random x values.
1, 2.
Okay, so let's pick 1. Penny. If I pick 1 and I plug it into this, okay, the instructions for this new bracket system is to round down to the nearest integer, or if it's already an integer, leave it. So what should we do with the 1?
Leave it.
Leave it. It's already an integer. So if I picked another integer, I'm going to leave some space and you'll see why. If I picked another integer, we'd still leave it. So those don't really change. We need to also check out something that's not an integer so to see how that's going to change. So what's something
1.5.
not an integer? 1.5. Dalton said 1.5.
4, 2.
Got to put the 1 there. Okay. What should we round 1.5? 1. Okay. I just used the word round on purpose because a lot of people want to round it up to 2, because if we're actually rounding according to the rules of rounding, we round up. But what do these brackets tell us to do every time?
Round down.
Round it down to the nearest integer. So if I had 1.7, still be 1. So let's try and get an idea of that picture. What about 1.9? Still 1. What about 1.999? Still 1.
What about 4.8?
4. We'd always round it down to the nearest integer. So 2 points we know for sure is 1, 1 and 2, 2. We know those points for sure. And I could do that with any integer. Guys,
Okay, I'm trying.
please be quiet. It's not just you. I've had to remind multiple people over and over again to be quiet. So please be quiet so I don't lose my temper. Okay? So if I did 0, we'd have 0, 0. Or negative 1, we'd have negative 1, negative 1. We know all of these points remain the same. Steve. So now we have to see what's going to happen with the rest of our graph. So we said 1.5, it's halfway between 1 and 2, is still 1. What about 1.7? Still 1. So right now we're still on 1 until what happens at 2?
Then at 2, it goes in.
Steve. At 2, it jumps up to 2. So here, just so we know where it ends, we have to put a circle to say, okay, it ended at 2, because we know the point at 2 actually jumps up to 2. So what's going to happen if we do 2.3? Still 2. So it's going to travel along, and it's 2, 2, 2, until we hit 3, when it jumps up to 3. Gerardo.
So when is that
So-
2?
All of them travel 1 to the right
Okay, I get that.
until they jump up to the next line.
To the end.
Dimitri. So can you see why this would be called the step function?
Yes.
Looks like we've made a set of steps.
Oh, wow. Wow. I think
I see it.
Looks like a set of steps. The reason they call it the floor function is because we're rounding down. And the reason they also call it the greatest integer function is because we find the greatest integer smaller than whatever number we're looking at. So it does have a lot of names. So this is what the floor function looks like. But we could also do some translations. I could take this entire thing and I could move it around. I don't know if it's all grouped together or not. Probably not. Nope. Back. So I could, if it was grouped together, I could actually move every single step over, every single step left. I could move every single step up or down. So if I have a picture of a graph, I can still do my translations. So let's look at, this is our last example. Practice A, problem 7. So we're still on the same page. Practice A, problem 7. So, looking at this, is the 2 inside the floor function or outside the floor function? Inside. Inside. So we have to think back to some of the other things we've moved around. We've also moved around quadratics. When the number was inside the parentheses on the quadratics, what direction did we move in? To the left. Sorry, I'm backwards from you guys, so I always have to think of which way is your
What,
left.
to the left?
To the left. If it's inside, it's a horizontal shift. And it was opposite of what we expect, so positive actually means go left 2. What if it was outside? Vertical shift, so we'd move up or down, but they didn't have a number outside, so we don't have a vertical shift. So we're taking that floor function and we're actually moving every single piece left 2 spots. So if I had this piece here, that was one of our pieces of our floor function, and I move it left 2 spots, I'd go 1 spot to the left, 2 spots to the left. I'm actually sliding it to the left. So when we're drawing, if we just have the picture, it's always good to draw the original. With the quadratics, we could do it from the equation, but with these ones, it's good to have the original drawn, and then just move the entire graph. So in green is my original function, which we also called the parent function.
Wait, so what did you really do with all those? You just go,
We're going to slide every single piece 2 to the left.
I don't know, but how do you get all those coordinates? Oh, that's from my previous.
Yep, that's what we did in our previous problem, was got the parent function for the step function. Oh, sorry. So, there's our original function. If I slide every piece left 2, I start here and I'd hop left 2 and draw my new step. We know this one also hops left 2, draw my new step. We know the rest will just follow.
So we go to the left because of horizontal shift.
We go to the left because it was a horizontal shift. If the number had been outside and we had a vertical shift instead, we'd move everything up 2 or down 2 or maybe 3 or 4, depending on what number they gave us. So vertical shift, we'd actually move everything. If this is my original and it said +2 outside, we'd go up 2 and just redraw it to above where we're at. And we can do that with any picture, not just with the step function. You just have to look really quick on page 278. We're just going to talk about it for like 20 seconds. On page 278, those are not step functions, but I still can do horizontal shifts or vertical shifts or horizontal shifts or vertical shifts, up, down, left, or right, with whatever picture they've given me. So like on problem 9, what direction should you move everything? -1 is that inside or outside the parentheses? Outside, so
Vertical
it's
shift,
down
down
1. Okay, we would just take the picture they've given us, drop it down 1. We just move every point down 1. So your homework for tonight is page 275 to 281. It's just that we had to kind of skip some pages, so it's anywhere in that set of pages. Problem 2, 8, 9, 11, 12, and 24. 2, 8, 9, 11, 12, and 24.